Good afternoon. I'm Rebecca Onashok with the Office of Space and Defense Power Systems, and I'll be discussing MS-RC-2 as the research topic area. I'll just briefly go through what our office does and what our major goals are, and then I'll step into what the research call that we're looking for this year is. The Office of Space and Defense Power Systems focuses primarily on designing, developing, building, and delivering radioisotope power systems for space exploration and for national security applications, although the focus of our topic today is on the space side of our work. We also support research, development, and design of fission power systems, but that also is not going to be related to the topics that we're calling for. The benefits of the radioisotope power systems work that we do is to enable customer missions in areas where they can't use other power systems like batteries and solar power systems. The radioisotope decay allows long-lived missions in space environments. We directly support NASA missions to the Moon, the Mars, and to the outer planets, and right now even beyond with the Voyager spacecraft. Our key research and development areas are looking for materials that are readily available and that can be used in the extreme environments of space. Again, we focus primarily on space science and on exploration. We maintain the capabilities to produce and deliver plutonium-238 and the power systems that go with them in between these missions. And we report to the Deputy Assistant Secretary for Reactor Technologies within the Office of Nuclear Energy. Most of our work is cooperative with NASA to actually provide the power systems and deploy them on various missions, and I'll go through a few of those in a moment. And then we also maintain ongoing capabilities and facilities at several national laboratories and manage contracts with the private sector to build and to deliver power systems. Our current major projects are the multi-mission radioisotope generator, which was delivered to NASA. The first one was used on the Mars Curiosity rover. We're also working on an advanced Stirling generator that would, if it's deployed, allow for much less plutonium usage for the same amount of power in various environments. It's under development now. And then also nuclear thermal propulsion technology and ongoing fission R&D. I won't go into too much detail. There are several charts on historic missions that we've supported using radioisotope power systems. The main usefulness of this is as a reference to help understand the various environments that we go to, the durations of missions, and just the general scope of these activities. We've had a variety of materials that I'll reference later that have been in use as far back as the Galileo mission mentioned in 1989. So there's a great deal of information out there about the power systems we build and where they've been deployed. The most recent two missions, one of them was launched in 2006. It's on its way to Pluto right now, but it uses a thermoelectric generator design that we no longer manufacture. However, a lot of the information on this, we do use the same heat source module, and so there's a great deal of relevant information about that mission. The most recent and probably the most familiar is the Mars Science Laboratory that's ongoing right now. On the surface of Mars, and that is using a generator design that we currently build and that we plan to continue to build. So when I get into some of the things that we're looking for in terms of insulation and so forth, this is our most current and recent example of what we've deployed. The key components and safety features of the radioisotope power systems are the plutonium-238 fuel, cladding that encases the fuel, and the graphite heat source that protects the fuel and the cladding. That graphite heat source is one of the main areas that we'll be discussing further. And then a power conversion system, which would be either that MMRTG or that advanced Stirling generator, the two that we're currently building. So when I get into some of the insulation materials that we're looking for, those two power systems are the best references. Our grander challenges, and these go beyond just what we're looking for in this call, we're always looking to enhance the safety performance of our systems, which would include the materials that we select and the various product and component characteristics. Always looking to improve performance, greater efficiency, reliability, and enhancing the different missions that we can support, going to different environments, for instance, and working on manufacturing processes to improve safety, to improve efficiency, waste minimization, improved cost, and so forth. As to what we are looking for in this research call, there are two main areas. The first is defined as specialized replacement materials. The aeroshell module, when I, in an earlier chart, showed the general purpose heat source module, we use an aeroshell material known as fine weave pierced fabric. It's been used for a very long time, and it performs extremely well for safety purposes, but it is difficult to manufacture. In addition, the manufacturing base for that, it used to be shared with other applications that are no longer applicable, and industry has moved on. They don't make this anymore. We have one vendor that we are continuing to use, but they have not committed to an ongoing production campaign for us. So replacing this material with something that's more readily available, perhaps easier to manufacture, but meets all of the safety characteristics that we're accustomed to is going to be very important to us. The specific work scope description is that we're looking for alternate materials for that aeroshell module to protect the radioisotope power system fuel during atmospheric reentry events. The particular characteristics of the material that we're looking for would include ablation resistance, thermal conductivity, structural strength, compressive and tensile, to meet or exceed the historical performance characteristics. Now that is not laid out in some very specific requirements document. The best way to find that out is looking through the research literature about the design and the development of the general purpose heat source module and its applications over the years to understand the unique combination of characteristics for ablation and for strength that we use for this. And it also it's also a thermal conductivity layer to move the heat from the plutonium out to the conversion system. So while protecting, it also has to move heat. It's a very unique material. The other area where we're looking for support in this call is on insulation materials. The two systems under development now, unlike the past general purpose heat source RTG, we have the two systems, the MMRTG and the ASRG. Both of those are what we call multi-mission systems designed to operate either in deep space or on the surface of Mars. And as part of that, integral to the system, we surround those sides of the heat source that are not transferring heat to the conversion system. We surround those with insulation materials. And those insulation materials have to survive in deep space or on planetary surfaces or any place where we might go in deep space. The broader the applicability and the broader the compatibility with different environments, the better. But we've also discovered that the insulation itself and surrounding the heat source can enhance the safety characteristics. If we have an insulating material that absorbs kinetic energy on impacts, it's an improvement over our already good safety performance. So again, we're looking for materials that are more readily available than some of the things we currently have, which right now we're using Microtherm and Min-K as the two main materials. So the development of alternate insulating materials that can survive for long durations over a variety of temperatures through a broad range of applications and can enhance our safety performance is what we're really looking for. And the work scope description pretty much repeats some of the same things. Anything you would look for in general spacecraft design, we're looking for here in addition to our safety characteristics, things like low mass, tolerance to space environments, and so forth. And because we are designing sort of workhorse systems to go to multiple destinations, the more space environments that it can survive in, the better. As a reference, I have an image of the flight MMRTG design. And the main purposes here, as you can see, both the red items in the center is a stack up of the general purpose heat sources, so you can sort of understand how those come together in a system. Although generally for this system, for accident scenarios, they're designed so that they can come apart for ablation and so forth, and that's documented well in the literature. The Min-K and Microtherm insulation are also highlighted on this diagram, so you can sort of see in this design where they go. We're not limited to just looking at these systems and these particular designs, but that's a good example of what we're looking for and how we typically use it. And that's actually all I brought with me. If we have questions, I went through it kind of quickly.
Are there any specific insulating materials that we should take under consideration?
No, again, the current state of the art is Min-K and Microtherm, so that's a good reference for how much kinetic energy we absorb and the various thermal characteristics. So any readily available material that improves on those would be considered.
There was mention in an earlier part of this webinar that this type of research would be transferred to NASA. Can you comment?
Both NASA and the Department of Energy do research in both sides of this, so it's not been transferred per se. Both agencies continue to do basic technology research for things that they need, and we also leverage what other agencies are doing.